Hey students, this video is going to go over gas stoichiometry. So there's two different kinds of ways that we're going to tackle these stoichiometry problems. First off though, I want to remind you that we use stoichiometry when we're talking about two different substances in the same problem. So when we were using that combined gas law last week, we were talking about changing conditions, but we were talking about the same sample of gas. We weren't changing what kind of substance we were talking about, which is why we didn't use stoichiometry yet. With stoichiometry, you would maybe have to find, starting with grams of carbon dioxide and then finding something about oxygen gas or something to that effect. Now, the way that we tackle gas stoichiometry is determined whether or not based on, sorry, that sounded really stupid. But anyways, we base what kind of stoichiometry we do on whether or not the gas is at STP or not. So read the problem. If it's at STP, all we have to do is stoichiometry. We don't have to do anything else because there's a new conversion factor. That new conversion factor is 1 mole of a gas equals 22.4 liters. So we would use that as any other stoichiometry conversion factor, like 1 mole is equal to the molar mass or that mole ratio. When it's not at STP, we would have to use stoichiometry and the ideal gas law, and you would have to determine which one you would use first. So let's first start with gas stoichiometry that's at STP. So in this case, it tells us that we're trying to find the volume of oxygen at STP that's produced by the decomposition of 0.600 moles of potassium chlorate. So let's go ahead and write our reaction first. We've got, and I think this is already in your packet, but I'll just pop it up here. I forgot this solid over here. All right, and let's go ahead and balance this. So we're looking for liters of oxygen, and we know the moles of potassium chlorate. Now, since it's at STP, we know that 1 mole of oxygen is going to be equal to 22.4 liters of oxygen. Now, this conversion factor can only be used for gases. You can't use them for solutions, only gases. So we're going to do some stoichiometry, and when we do stoichiometry, we start it by same way that we always start stoichiometry, 0.600 moles, that's our given, of KClO3. We multiply it, since we're already in moles, we're going to go ahead and use that mole ratio. So 2 moles of KClO3 and then 3 moles of O2 on the top. And then we're looking for the volume of oxygen. So since we have moles of O2 on the top, we have moles of O2 on the bottom. We already used our coefficient, so we're back to 1. And we know that 1 mole of O2 is equal to 22.4 liters. So you can see I'm using that last conversion factor just like any other times that we've done stoichiometry or mole conversions. So I can go ahead and calculate. So I've got 0.6 times 3 divided by 2 times 22.4. I want 3 sig figs because of my given. So my answer would be 20.2 liters of oxygen. Okay, and just like that. Now, when it's not at STP, you have to really analyze your variables so you can figure out what to do with the information that you have. So list out all of your variables. When you're looking at your variables, pay attention to what substance is talking about. So is that mass talking about, a reactant or a product? Is the volume talking about O2 or is it talking about CO2? Because that's going to be important in telling you that you need to do stoichiometry at some point to switch. Now, if you have all of your gas law variables, so if you're given the pressure, the volume, and the temperature, you're going to use the ideal gas law first in order to find the moles, and then you'll do stoichiometry to switch to the other substance and find whatever it is that you're looking for, whether that be the moles or the grams. If you're missing one of those gas law variables, so if you're trying to find pressure, temperature, or volume, you're going to do stoichiometry first in order to find the moles of that substance you're trying to find the gas law variable of. And then you'll use the ideal gas law to find that missing gas law variable. So let's take a look at this question here. I think you have the reaction in your packet, so I'll just write it out really quick. So we have potassium iodide reacting with chlorine gas to produce potassium chloride and iodine. So we're looking for the mass of iodine. We know that we have the volume is 7.00 liters of Cl2. We have a temperature of 37 degrees, but we have to get that into Kelvin. So we have to add 273, so it's 310 Kelvin. And we have a pressure of 110.4 kilopascals, but we can't use kilopascals. We have to convert that into atmospheres because we have to use atmospheres in the ideal gas law. So 110.4 divided by 101.3, we've got 1.090 atmospheres. So in this particular example, we have all of our gas law variables. So that means we're going to start by using the ideal gas law. So we're going to do our 1.090 atmospheres times our volume. It's going to equal our moles times our gas law variable, or sorry, gas law constant times our temperature. And I'm not going to round to sig figs until the very end. So in order to solve for n here, we're going to take our left side and divide it by our right side. So I'm going to have our pressure that we just calculated times 7 divided by 0.0821 divided by 310. So that means that our moles are going to be 0.2997. I'm not going to write all of these up there. Moles. Now, what are these the moles of? Since we had the volume of Cl2, that means that these are the moles of Cl2. And we're not looking for the grams of Cl2, we're looking for the mass of iodine. So we need to use stoichiometry to convert from this many moles of Cl2 into grams of solid iodine. So we've got to use our mole ratio down here, and I've never balanced the reaction, forgot to do that. So we have Cl2 on the bottom, so that is 1 mole of Cl2 here. We have 1 mole of I2 here, 1 mole of I2 here, and our molar mass 126.71 times 2, so our molar mass of iodine is 253.42. If that's slightly off, I apologize because I'm not looking at my periodic table. All right, so I'm going to take my moles that I calculated, times it by my mole ratio, which is just 1 to 1, times it by my molar mass of solid iodine. Now I'm only going to be able to get 2 sig figs on this question because of my temperature. So my answer is going to be 76 grams of iodine. Sorry, I don't know why that was. Here we go. All right, let's take a look at the next question. So how many liters of oxygen gas will be required at a temperature of 305 Kelvin and 3 atmospheres of pressure to consume 25.0 grams of methane? So I know I have to write a reaction and do some kind of stoichiometry because it's talking about oxygen and methane. So let me go ahead and write my reaction. CH4 plus O2 yields CO2 and H2O. So I'm going to have to balance that reaction. There we go. Now I want to list out all of my variables. So I'm looking for the volume of oxygen. That's my unknown. I've got a temperature of 305 Kelvin. I have a pressure of 3 atmospheres. And I have a mass of 25.0 grams of methane. All right, so we have to find one of the gas law variables. We're trying to look for the volume. So that means we're going to have to start with stoichiometry. Now, where are we going to want to take our stoichiometry to? Well, we're looking for the volume of oxygen gas. So we want to take our stoichiometry to moles of oxygen gas. Now, why are we going to go to moles? Because we're going to have to use the ideal gas law next. And moles goes into the ideal gas law, not grams. So we start with our 25.0 grams of methane. We're going to have the molar mass of methane down here at the bottom. 1 mole of methane up here, because molar mass always equals 1 mole. Then I'm going to use my mole ratio, 1 mole of methane, and then 2 moles of O2 up here on the top. So I've got 25 divided by 16.05 times 2. So that's about 3.12 grams. Now I might write, not grams, moles of O2. I might write a rounded value here, but I'm going to go back and use my unrounded value in the calculator. Now, let's go ahead and plug that into PIVNERT because we have to use the ideal gas law next. So we have our 3 atmospheres. We're looking for the volume. We have our moles. We have our ideal gas law constant. And then we have to put our temperature in here. It was already in Kelvin, so we did not have to convert. So I'm going to take my moles of oxygen that I just calculated. I'm just going to use that unrounded value in my calculator, times it by 0.0821, times it by 305, and then I'll divide by the 3 to get volume by itself. Now I'll be able to have 3 sig figs in this answer. So my answer would be 26.0. I'm solving for volume. And in PIVNERT, that unit is going to be liters. And that's how you use the ideal gas law and stoichiometry. So if you have any questions, go ahead and let me know as you work out the other problems in your packet.